Hi, welcome to the sixth live session of Quantum Topology 2 today. Today first we'll discuss some problems regarding simulation actions, and then if time permits, then we'll go on some problems regarding simplification and so on. Okay. So, um, okay. So let's start from some problems regarding simulation actions and all. Okay. So first problem is as follows. And it starts from some basic problems and gradually we increase its difficulty level. Okay. And also we should try to go with some one point computation of the spaces. Okay. Just hold on. So okay, so let's start with the problem from 1 point computation. So first question is, mm, can you have a disconnected space whose 1 point computation is figure 8? Hold on. The first question is, can we have one discrete space whose Warner compactification is figure 8? Figure 8 means this object. This figure 8. So we need to find a discrete space. Warner compactification is figure 8 means we need to find a space in which if we attach 1 point, then it will be a figure 8. Okay. Okay. I'm in this portion because this project is not properly actually. So can we have one discrete space? We want to compute figure 8 means what? So for this, what we what we can do? So what is the possible idea? So basically we need to go in a back track. That is, we need to remove 1 point from the figure 8. Okay. So if it is a figure 8, okay. So in how many ways we can remove 1 point of figure 8? So from here we can remove 1 point. From here we can remove 1 point. If we do consider this, then the resultant space look like this. And if we remove this point, the resultant space look like this. Okay. This is same as open interval. We can circle attached to 1 point. This is what disjoint to open interval. Okay. So this is a space disjoint whose one-man computation is figure 8. Yeah, so this is a solution. Okay. And minded that this space has two components. Okay. So consider the next problem. Can we have a disconnected space with more than components whose 1 point computation question is, can we have a disconnected space with more than two components? Sorry, no. With one-to-one complexification is figure 8. Is it possible? So, um, I mean, what is the idea? So this figure 8, we need to remove one point such that after removing the point, the space becomes three components. Now, is it possible? We can remove one point from here, from here, from here. But if we remove one point from here, this gives space like this, which is connected. So this will not work. If you remove one point from this middle, then this the resultant space will look like this, which is disconnected, but it has only two components. But the question is says that the resultant space will have more than two components. So this example will not work. Okay, if you remove this point, then obviously it will not work. So basically the point is, from figure 8, if we remove one point, then at most we can get two components. So we can't have any space having three components with one point computation is figure 8. So the answer is no. This one. Yeah. So the next problem. So the next problem. Okay, let us think first. Okay. Give an example of a space which is house draw but not regular. We need to find example of space with house draw but not regular. So so give an example of space with house draw but not regular. Okay. So how to find such an example of space? So does the usual topology will work? No, because usual topology is obviously regular. Does the lower level topology will work? We don't know, we need to think about it. Does R with K topology work? We don't know, we need to think about it. Okay. So, what about the lower limit topology? You might have known that lower limit topology is actually normal. So it is regular. But what about R with K topology? What about this? So, uh, the reality is that R with K topology is not regular. But how to do it? So for this, what we need to do? For this, we need to find a closed house to Rk and a point in Rk, because it does not belong to closed set, and we need to somehow show that we can't separate the point and the closed set by open neighborhoods. Okay. So in this situation Rk, consider the set K, which is closed in Rk, and consider the point 0. Now the claim is that the point 0 and K can't be separated by open subsets. Okay. So how to do that? So firstly, let's try to develop intuition. I mean, whatever the intuition in this situation, that will be actually the answer. But we need to somehow develop intuition first. So just wait a minute. So so uh, so we need to obviously prove it by the method of contradiction. So suppose there exist open sets. I mean, sorry. Let the set 0 and set capital K can be separated by disjoint neighborhoods. So call them U which contains 0 and V which contains set capital. Okay. Now observe something. So we'll have a base element like this contained in UK, or the base element should look like this contained in UK. Okay? But for the V, uh, yeah, okay, so forget about this first. Okay. Now we have already assumed that the neighborhood distance, so intersection is equal to empty. Okay, but if the disjoint neighborhood is of the form open AB and contains 0, so basically it Barkerian property, this intersection is empty by Archimedes property. So the open neighborhood must be of the form this. So basically 0 belongs to minus the subset of okay. Now From the set capital K, take a point 1 by n. Okay. So this belongs to some open interval series which is sub of B. So how the image looks like is 0, it is open A, B, it is some 1 by n, it is C, it is D. Okay. Now what we will do? We will now we can consider the point 1 by n plus 1 which is less than n. So the point 1 by n plus 1 either lie here or lie here, whatever it is. So if we choose any point z which is greater than max c comma 1 by n plus 1 and which is less than 1 by n, then the point z belongs to u and v both. So this will be non-integer. So that's the contradiction of the choice. So that's why R with K topology is not Hausdorff. Okay, this is the full out. Yeah. So now okay. Okay, so now consider let's go with some problems for the separation. And first, okay, so first let's start with something known as proper maps. For the definition, so let F from X to N be closed, continuous, surjective, such that F inverse singleton Y is compact for all Y belongs to Y. Then F is say proper map. Yeah. So one way is to check that, for example, polynomial map is a proper map. Another example is if it's compact, Y Hausdorff, then um, hi, am I audible?
Yes, sir.
Okay. So that one. And can you see the screen? Can you see the screen?
Yes, sir.
Okay. So So first let me tell what I have discussed so far. Because so first today we have started. Actually, today first I started with some one example from the water complication. The first question was that um, can we is possible to get a discrete space whose one-time computation is figure 8. Okay, so for that what we have done, so basically we need to calculate a space with one point computation is figure 8, right? So basically in order to construct the space we need to go backward, that is we take figure 8 and then remove one point from figure 8 in order to obtain some discrete space. Now observe in the picture that this picture that if we take 2 points, I mean if we remove the point from one circle itself, then the resulting space is connected. So this will not work. But if we remove its common point, then the resulting space disconnected. So this is the disconnected space with one part of compactification is figure 8. Okay, this is the first problem that we've done. And the second problem was that is it possible to get a disconnected space with more than two components with one part compactification is figure 8. So basically, we need to somehow argue that from figure 8, if you remove one point from different positions, it's possible to get one discrete space having more than one component. But if you observe the picture of figure 8, so you can remove one point from the circle or one point from the common, I mean that joining point. But anyway, if you remove one point from the circle or one point from the joining, then you can get at most two components. So figure 8 can't have any space having more than three components with one word compactification sphere. Okay. So these are the two problems that we discussed. And also in the last session, some learner wish to understand the argument of why R with K topology is not regular. That's why we discussed today that R with K topology is regular. The almost same argument. Okay. So okay, so first please go through these first few questions, figure 1 by quantification concerning the figure 8. Then first let's go through these two answers and let me know do you have any confusion regarding this. Please take your time. If you have any issue in understanding the solutions, please ask question. Because this problem is meant to this question is meant to problem solving. Please ask, don't hesitate.
Sir, can you please explain the problem number one once again?
Yes, so yeah, okay. So let me write it down separately. One second. So in problem number one, the question is that is it? I mean, can we construct a space? I mean, can we construct a disconnected space whose one point compactification is figure 8? So do you understand the question first? We need to find a
Yes,
disconnected space. Yeah, okay. So what we need to do? We need to find some such space such that attaching one point gives something like figure 8. So in order to find that space, what the easiest way is to do? I mean, if the space x, then if the space x disjointed at some point, and then we get the figure 8. So from the figure 8, we can remove one point in order to get that space capital X, right? This is what we need to do. Understand?
yes,
So if we consider the picture of figure 8, so we can remove points from this circle, from the joining point, or from this circle. Okay, but if we remove from the right circle, the resultant space will looks like this, and if we remove point from this joining, then resultant space will look like this. Okay, but the thing is we need to find this kind of space, but the thing is first this one is connected, right? So this will not work, but the if you remove point from the I mean, from the common joining portion, then this resulting space is disconnected, correct?
yes,
So that's why this is the space so that it's one way computation is figured. That's the answer. You understand?
yes.
Okay. So the same question is one second. Same question is that can we have a disconnected space? So observe one thing that the first problem, the resulting space, that disconnected space has two components, right? So the second question obviously is the obvious in nature is that can we have discrete space with more than two components whose one-point compactification is figure 8. Okay, so think it in similar way and try to understand that if we remove one point from the figure 8, then we can't have any space having more than two components. I mean, it is almost similar, but please think about it. If you have any issue, please think, or if you don't understand, then please ask.
Yes, sir. Yes,
Okay, so, oh, so you understand the problem too, right?
yes, sir.
Okay. So the problem three is that here we are trying to find an example which is house drop but not regular. Okay. So okay, so I think it's better to repeat the argument again. So what we have done here, anyway, I mean, so first of all, can you remember the argument that R with K topology is not regular?
Yes, sir.
Okay. Okay. So let's go to some new thing. So the new thing is that proper maps. Okay. And using this, we have some problems regarding compactness and regarding separability. Okay, so first let's understand what does mean by proper maps. So suppose if x to y is B closed continuous surjective, such that if inverse singleton y is compact for all y, then f is said to be proper map. This is a definition of proper map. Okay. For example, polynomial map is a proper map. I mean, polynomial map is a proper map. I hope you understand why it is obvious, right? Because anyway, because it's a polynomial map like x, x squared, x cubed. These are all closed maps, correct? So, and inverse of compact is compact, obviously. So, yeah. So, polynomial is proper map. And similarly, if x compact, y house drop, then any map f x to y continuous plus adjective is a proper map. So, this is a definition of proper map. Okay. So now, oh, the first problem is that
Sir,
yes, yes.
in the definition of proper maps, here if there is a condition that if inverse y is
Com-
compact for all y. So here we are not considering where f is injective or not, because if f will not be injective, then there is possibility that for some y f inverse y will be multi-valued function.
Yes, yes. We are not taking consideration injectivity. I mean, F can be any map. In the, I mean, F can be any map. That's not the. It may,
Yes,
if it is injective, then obviously it is proper, right? It may not be injective, then if F inverse Y is compact for all, then it will be proper map. Okay.
okay, sir. That means we won't be bothered about whether the
Right.
inverse of any point be one valued or multiple valued.
Yes, I mean,
Okay.
if it is single valued, then obviously compact, right? So obviously, if inverse Y compact for all I means most probably the chosen function is not injective, right?
Yes.
Yeah. So first problem is that so you know that continuous image of a compact space is compact, right?
Yes.
But converse is not true. It's not difficult to construct example of it. But converse is true under certain condition. So wait, let me see the statement first here. So that is if F is a proper map and Y compact, then X compact. That is, if we assume the properness of F, then write the codomain compact implies domain compact. Okay. So this is the fact. First, you try to solve this. That. how to show the compactness of F using X using properly separated compact system. Plus try to show. Then I will do the problem. I will solve this. But first you take your time. Think about
Okay, sir.
it. Yeah.
Sir, if we will assume F as a proper map, then we will assume it as surjective as well, or not?
Yes, a surjective. Proper means continuous closed surjective.
Okay, sir. Then since Y is compact, that
Hmm.
means we can take F inverse Y.
Yes.
Since F is proper map, so F inverse Y will also be proper, which will be equal to whole of X.
No, no. I mean, it's a proper map. So F inverse singleton Y compact for all Y, right? Finite union of compact sets is compact, correct? But arbitrary union of compact set may not be compact, right?
Okay, sir. Actually, I in the notes there is something written that if F is a proper map, then inverse image of a compact subset will be compact.
Ha,
That's
did
why
you?
I like yeah.
Okay. So is it a theorem in the notes?
Yes, sir. Something similar is there. I'll have to see.
Okay, actually it is actually a problem. And so anyway, since this is theorem, so there is no point to this problem. Okay. So mm, okay, so yeah, I understand that it's a theorem. Okay, so forget about so leave this problem because it's theorem there. Okay, so that's so yeah. So okay, so let's do this problem. So suppose p x to y is a closed continuous adjective map. That is proper map. Okay. Show that if U be an open set containing P inverse singleton Y, then there exists a neighborhood W containing Y such that P inverse W subset of P is given to be a proper map. Show that if U is an open set containing P inverse Y, then we can find a neighborhood W containing Y. So P inverse W is inside P. It's a tricky problem, so take your time, think about it.
Sir, here we have assumed that only U is open.
Yes, yes, U is open, and we need to find a W which is an open set and sorry open set containing Y. So the P inverse is subset of P inverse will be subset of U. Yes. who has joined late, please let me repeat the question for her. So the question is that suppose P is a map from X to Y which is closed, continuous and surjective map. Now we need to show that if U is an open set containing P inverse Y, then there is an open set W containing Y such that P inverse W subset of U. You can directly solve this question without knowing what have I till now. Okay? So let's try to solve this problem. This problem does not use any theory that we've discussed till now. So directly, let's try to solve this problem.
Uh, sir,
Yes,
since P inverse of a singleton Y is contained in U, which is open,
yes,
and uh, so the complement is closed in X, and since the map is a closed map, so P of U complement is closed in Y, and it does not contain the element Y.
so you are saying that P of U complement closed and Y does not belong to this. Right. Then
Uh, So if we again complement, because it is a closed, so its complement is open in Y and
yes,
it contains the element Y.
and okay, yes,
So if we define the set W is equal to this, and so we need to prove the inverse is
yes,
contained in this.
yes, perfectly, very good, very, very nice, right. Yes,
So
very good. Yes, then the rest of the question is obvious, right? That's fine, perfect, very nice. I mean, the W is an open neighborhood. I mean, the point is that I understand that P U complement the open set contains Y, so we can get a neighborhood W contains Y. So the W is contained in the P of U complement whole complement, and then you need to show that the P inverse W subset of P, and that's almost obvious. This is what you are trying to say, right? This is what you want. You are giving the argument, right?
yes, sir.
Yeah, good. Yeah. So nice. So, and small extended version of this problem is the following. Show that if B be any subspace of Y such that P inverse
Uh,
B,
uh, so,
yes, please.
uh, sir, in the last problem where we use the surjectivity,
Uh, Subjectivity. So, why it is subjective? No, actually, in this problem, there is no use of subjectivity. Only closeness is needed. Actually, the whole problem is a big problem. So I am giving the problem part by part. Okay. So that's why in the question itself, I put the statement close, continuous, subjective. But for the first part, we don't need any subjectivity. Only closeness is sufficient. Okay. Understand?
Okay, sir. Yes, sir.
Okay. So the small extended version of this is that if B is any subspace of Y, okay, if any subspace of Y, then such that P inverse B is contained in the open set U, then there exists an open neighborhood W containing B such that P inverse W subset of U. In the first problem, it was a point, and in the new problem, it is the point is replaced by some random arbitrary sets. Sorry, by some arbitrary sets. Okay, so yeah. So similar, we can give the argument, but I mean, you can directly give the argument, but using the first part, do the next part. So that's the point. Okay. So try to solve this using the first part of this problem. Okay. Take your time. Think about it. and you were able to solve it. You need to use the first part. That's the only thing you need to do.
Sir, is a P is a closed map?
No, no. Sorry. What did you say?
Uh, in this problem, is it a P is a closed map?
Yes, yes. P is a closed map. P is a closed one.
So then we can again assume the complement of U
Um,
and P inverse of B does not intersect U complement,
mhm.
and because U complement is closed, so P of U complement is closed, and B intersects P of a U complement of complement. So we it is an open. It will become an open set. Then if we define W to be the set,
No, no. The thing is that from the first problem you have only one point. Okay. So for that thing you can get open the W containing that point. Okay. But here the B is a whole set. So for each point you will get a neighborhood W, right? Correct.
okay.
So then what to do? I mean you are almost there, but then what to do?
So if we take for each element B of a B
Yes.
and define W of a B as a
As in okay. So basically um so if we take each for each y belongs to B, here exists WY containing Y such that P inverse WY subset of U, right? Now, so for each Y belongs to B, we are getting this. So now, obviously, B subset of union WY, Y belongs to B. So obviously, P inverse B subset of union P inverse WY, and which is subset of U. So that's why, and this arbitrary union open set is open W. Okay. So P inverse W, sorry, I mean B subset of this and P inverse of W is a subset of Q. No need of this here. Do you understand? I have put messed up in order to make it. So basically what we have done, sorry, let me write it clearly actually. So from the first problem, for each y belongs to B, we will get an open neighborhood WY containing Y such that P inverse WY is a, sorry, mm, P inverse WY is subset of uh, for subset of U. Okay. Now take W is equal to union of WY. Y belongs to Y. So the Y belongs to B. This implies B is contained in W and P inverse W subset of Q. So this is what we need to do. Do you understand? Do you understand?
yes, sir.
So having said this, some solid problem. That is, now comes to the main problem is that if P x to Y closed, continuous, surjective, and inverse Y compact for all Y belongs to Y, this implies then show that Y compact implies X compact. So this is the, I mean, usually domain compact plus codomain compact, but converse is also true under this condition that if it is a perfect map, then the right side compact is like the left side compact. Oh, sorry, I just remember that another learner already told that it has been solved by in the it, in the note class note it is given as theorem. Sorry, I forgot. Okay, so leave this problem. So yeah, so the problem actually was thought is that so if px to y closed continuous surjective, then show that if x normal, then y normal. Okay, I mean in general normality may not be preserved and continued. Okay, but if p is the first one surjective, x normal implies y normal. Okay, for this you obviously need to use the first two parts, that is namely this part and this. You need to use somehow. Okay, but okay, first try to solve this. Okay, so we need to show that y is normal. So first you need to show that y is Hausdorff, then only you can go for the rest of the portion. Okay, so first try to show that y is Hausdorff under this condition. Let's think about it. It is not difficult, but it is tricky. Please take a time, think about it. Are you able to show that Y is house draw?
Sir,
Yes.
sir, I tried in the way like I've considered two disjoint closed subsets of Y.
Hmm.
Then, sir, since P is continuous and A and B both are disjoint, so P inverse of A will be closed as well as P inverse B will be closed
Yes.
and they will be disjoint as well.
Yes. Okay.
And sir, both are the subsets disjoint closed subsets of X, and as X is normal, so we will get two disjoint open sets U and V such
Yes.
that P inverse A will be subset of U
Yes.
and P inverse B is a subset of V, where U intersection with V will be uh, 5.
Yes. Right. Okay. So
So,
yeah. So that's five. Very nice. So
sir,
what about yes. Yes. Tell.
so P inverse A subset of U will imply A is subset of image of U under P and B is subset of P of V.
No, no, one second. Can you please do it after that? P inverse A intersection P inverse B empty. After that, can you please speak? So P inverse A intersection P inverse B empty. After that, can you please speak?
So that means they are disjoint as
Yes.
well as closed subsets of X, where X is a normal space.
Yes. Yes.
So, sir, by normality of X, we will get two disjoint open subsets containing A and B. I assume them as U and V. So
Okay.
P inverse A is subset of U and P inverse B is a subset of V.
Yes. Okay.
So P inverse A subset of U will imply A is subset of P of U and B is subset of P of uh, V.
Okay. So
And, and
P is
sir, since
P is given to be closed only, right? P is not given to be open. Correct.
yes sir, but
Yeah. But but tell.
sir, since P is a closed map, that means we can we consider that P inverse is a continuous function.
Yes. Basically, this is what we have done in the first two portions. That is, if B is any subspace of Y such that P inverse B subset of U, then we'll get any open number containing B such that P inverse U P inverse W subset of U, right? So in the current context of normality, you already have P inverse A subset of U1, P inverse B subset of U2. So we'll get a neighbor W1 containing A such that P inverse W1 subset of U1 and neighbor W2 containing B such that P inverse W2 subset of U2. Now since U1 U2 intersection empty, so W1 intersection W2 equal empty and W1 contains capital A, W2 contains capital B. You understand?
Yes sir, but sir, I didn't understood where my solution
No, no, your solution is correct,
implies.
but the only problem was that P of E1 may not be open, right? I mean, need not be open. That is the problem.
Yes, sir. Sir, so here I am, sir, as you said that P is a closed map.
Yes, yes.
So that means P sends every closed set to a closed set. So if I will consider the function P inverse as y is a surjective, so if we will consider the map P inverse, then P inverse
One second. First of all, P inverse as a map does not make sense because P is not an injective map, right? Correct? Am I right?
oh yes sir.
That's why. for this situation, it is not given me injective. So this situation, inverse doesn't have injective. So in that way, it will not work.
Okay, sir.
Yeah. So you have done the normality portion, but in the definition of normality, first the space is assumed to Hausdorff, right? Correct.
Yes, sir.
So you have done the normality part. Now, similarly, try to show that y is Hausdorff. Then only the solution will be complete, right? So first try to show. Now try to show the y is Hausdorff. Almost similar, but not. I mean, it's tricky. So show that y is Hausdorff.
Sir, by this surjectivity, we can prove it Hausdorff if we take any distinct element in Y because it is surjective, so it has an inverse image x1, which is the inverse image of y1, and x2, which is the inverse image of y2. So,
Yes.
because x is normal, so suppose A and B, which are disjoint closed set containing x1 and x2.
Sorry. It's.
Uh,
Can you please repeat?
uh, so Sir, because X is normal, so suppose A and B are the disjoint row set, so that X1 is in A and X2 is in B. We choose a closed set
You
which
can
contains X.
uh, you can choose the disjoint closed set x1 itself, right? Because x1 is normal, so the house drop, so singleton is closed, right? So you can take the choose the set
Uh,
x1. Yeah. Then
and the map is closed. Okay. So there exists an open set because of X is normal.
yes.
So X1 is contained.
Okay. Then you need to find neighborhood around y1 and y2 somehow. And you got the neighborhood around x1, x2, the inverse images. Now think about it.
Yes, sir. Uh, mm, so, because uh, X1 is a closed, the singleton X1 and X2 are closed, and X is normal. So there exists an open set such that X1 is contained in U, and X1 is nothing but the inverse image of a singleton Y. So in in the
What
starting, we
what you have said, x1 is nothing but the inverse image of.
yes, sir. We in the beginning we assume that y1 and y2 be the distinct element of a y, and it is a surjective. So the inverse image of a y1 is equal to x1,
No,
and
it is not.
y2.
No, it is not equal to x1. First of all, y it is given to surjective only, not the injective. Okay, so its inverse image may contain more than one element, right? So you can only take an
Yes,
element from P inverse y1. Okay.
okay, sir. Then uh, using the normality of x,
Yes.
there exists an open set which containing x1. So it contains the inverse image of a singleton y1.
It contains one inverse image of singleton, only one inverse image, not the whole inverse image. I mean, x1, you contain x1, okay, so P inverse y intersection and non-empty. That's what we can say, but we can't say like the Q subset of P inverse y. This is not we can't say. Understand?
No, sir. P inverse is contained in U. The P inverse, the singleton is contained.
Uh, no, P inverse y. Why P inverse y is contained in you? I mean, P inverse y, one element of the P inverse y is inside you. Okay, but all elements of P inverse y may not lie inside you. Correct?
Uh, yes, sir.
Yeah. So I mean, you whatever doing is restrict to only one element, but P inverse y may contain more than one element, right? So P inverse y may not lie fully inside you. So that's the point. Okay.
Okay, sir.
So the argument goes as
So,
follows. Yes, please.
sir, then if the singleton P inverse of y1 is belongs to be U,
Hmm.
so we use the first problem that if P inverse of U is belongs to the open set, there exists an open set W in Y containing Y,
Hmm.
so that the inverse image of W is contained in U.
Can you please repeat the argument? Actually, I just put
So I am using the first problem, which was from P from X to Y is a closed continuous and surjective, and the inverse image of a singleton Y is belongs to be an open set U.
yes. Okay. X1 belongs to you and X2 belongs to B. Okay.
So then there exists an open set W containing Y such that the inverse image of W is contained in U.
Okay, right.
So if we take the
Yes, perfect.
because
Yes, right. Now you're on track. I understand what it meant. So the same goes
so,
with W2, W belongs to Y2. Then you are going to take the all possible unions, right? I mean, obviously, this is
no,
what is.
yes sir, and since Y1 and Y2 are distinct, so we can prove W and W2 are disjoint open set.
Yes, very nice, very good. Yeah, this is what the argument actually is. Good. So, nice. So, okay, so for the next problem, it is almost similar. So, Px to y, now given, it is given to be closed, continuous, surjective, and P inverse singleton y is compact for all y belongs to y. Okay. Show that x regular implies y regular. Show that x regular implies y regular. Well, this problem is like the previous problem, but it's quite trick obviously. So think about it. First, try to show that y is house drop. Y is house drop. Yeah, y is house drop actually from the previous part of this problem. So you can realize y is house drop. Now try to show that y is regular. Are you getting an idea? Are you getting an idea how to approach? Okay, so okay, um, so the solution goes as follows. So, firstly, why the house top? Okay, so we already have that. Now let's see subset of y be closed, and y does not belong to C. Okay. So then, in order to show the regulator of y, it is enough to separate the closed subspace P inverse C by this triangle. So first tell me, is it do you understand this thing or not? So we are taking y to outside of C. Now in order to separate of y and C, we only need to somehow come up. I mean, someone need to show that the fiber P inverse y and the closer P inverse C can be separated by disjoint operation. This is what we only need to do. If we can do, then what we can do? I mean, if we can do this, if we're able to show this, then we can then use the part 2, namely this part. Then we can directly use this part. Then this thing will solve the rest of the problem. Okay. So we only need to come up. We only need to show that P inverse y and P inverse C can be separated by disjoint operators. Now try to show this. I mean, this is a hint actually. Now try to show this, that P inverse y and P inverse C can be separated by disjoint operators. And of course, you need to here is the regularity of x. You take your time. Okay. Let's unblock the fund. Yeah, so are you able to get this? I mean, how to separate fiber P inverse Y and process P inverse C?
No, sir, I'm not able to see.
Okay. So, solution goes as follows, that so if we take any point belongs to fiber P inverse Y, and now since so this point X does not belong to this closed P inverse. Okay, so uh, we will get an open set U containing Y and an open set P containing P inverse C, so that U intersection is empty. Right. Now, I mean Ux containing X, but U regularity. Now take U to be union of Ux. X belongs to P inverse Y. So then, I mean, Ux, and then this implies U intersection V is empty. Okay. And obviously U contains P inverse Y because each UX contains each fiber of P inverse Y. Okay. So I mean, so we get an open set U containing P inverse Y, open set V containing P inverse C, which is, and their intersection is empty. Okay. So so by the problem 2, there was an open set W containing Y such that P inverse W is subset of Q. Okay. And W2 containing C such that P inverse W2 subset of Q. Now U intersection V is empty. This implies W1 intersection W2 is equal to empty. And this is what, I mean, this is what the regularity is. And yeah, that's the solution. You understand?
Yeah. Sir, we're taking X belongs to the UX.
Sorry, can you repeat?
Say, where we use the compactness of P inverse Y.
Compare with P inverse Y.
Yes, sir.
Yeah, yes, yes, I forgot to mention. Uh, one second. Okay, let me read the argument this one. Okay. Sorry, hold on. Okay, yes. Sorry, there is a slight mistake in the argument. Sorry for the, thank you for the pointing out. Sorry for the mistake. So basically we have started with Y belongs, X belongs to P inverse. Okay. So we'll get a neighborhood Ux containing X and a neighborhood P X containing P inverse. This are the Ux intersection of Vx equal to empty. Okay. Okay, right. Now P inverse was will be compact. So now since Ux contains X, so P inverse U, its one open cover is union of Ux. Okay. So we can have only finitely many subcovers. So P inverse Y is basically Ux1 union dot 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 Uxn. Sorry, Uxn. Okay. And for each Uxi, you already have Uxi intersection Vxi is empty, and each Vxi by construction, each Vxi contains the set P inverse C. Okay. Now take U to be this union U and V to be the intersection Vxi I0 1 to n, then capital V contains P inverse C and capital U contains P inverse Y, and due to this construction, U intersection V is empty. So the compactness has been used with the following: that P inverse Y subset of arbitrary union, so P inverse Y is a finite union, and so corresponding each UXI we have finite number of VXI, and in the each UXI we take the union which covers the P inverse Y, and since each VXI contains P inverse C, so we take the intersection VXI which contains P inverse C, and then each UX intersection VX is empty. So by this construction, U intersection V is equal to empty. Now we need to use the second part, that is, yeah, you contain P inverse Y, so you can get W1 contain Y, W2 contain C, such that their intersection is empty. Yeah, so this is the right way to understand. Sorry for the mistake.
Yes, sir.
Okay. Now, solve this one problem. So let f(x) to y continuous plus, it's continuous plus, let y show that although x belongs to x, so that fx equal to gx is closed in x. The question is that if x2 is a continuous map, y is given to house stuff, show that for each x belongs, show that the set x as the x, fx will just is closed in x. So this is the question. This is what you need to show. It is very easy problem, but think about it if you don't know already. Are you able to solve it?
So, so
Yes. Sorry, can you just repeat? I did not hear what that you think that is what you just said.
Sir, I am trying but not able to complete. Sir, because we have to prove that it is closed in X. So if we prove its complement is open in X, so,
Yes. Yes.
uh, and the complement is defined at those points where both are not equal.
Yes. Right.
So if we take any point in the complement, so fx not equals to the gx, and y is however, so there exists an open set, so that fx is in u and gx in v.
Yes.
So after that, I did not get open neighborhood of x, which is contained in that set, the complement of x.
You are almost done. That U intersection V is empty by the Hausdorff condition of Y. Right. Correct.
But sir, x belongs to the both set f inverse of u as well f inverse of v.
Ah, yes. That is not a problem. What you need to show that if it's this set, then you need to show that its complement is open. I mean, here you need to show something is open. You don't need to separate anything, right? So you need to, I mean, if you're taking any set from S complement, so if it's not good, you need to keep some open neighborhood inside S complement. That is what we need to do, right?
sir, sir, if
Yes,
we
sir.
sir,
Yeah.
I have also taken in a same way, sir. But sir, if you will take the that p, sir, I have taken p instead of x and up, sir, sir, like if we will take f inverse of u and g inverse of v, then
Yes.
x will belongs to both of the sets, and since f and g both are open it's continuous, so f inverse u will be continuous and g inverse will be sorry open.
Yes,
So
right.
this
And
is a
yes,
open
yes, you are right. The F inverse is G inverse V, and you need to show that it contained in the S complement. Right.
yes,
Then only we are done. Now, I think it is almost obvious that F inverse U intercept G inverse V is lies in the S complement, right? That's
yes,
all.
sir.
So that's what the solution, right? Also, it can be done in
Uh,
a yes, yes, please.
sir, but f inverse of u intersection g inverse of v, it will be empty set because u and v does not intersect.
No, U
It
and V is
must
empty.
have to be.
U and V is empty. That is right. So this implies F inverse U intersection F inverse V empty and G inverse U intersection G inverse V empty, right? But we have done F inverse U intersection G inverse V. Okay, understand? I mean, that's the point. Do you get it? Do you get the point?
Uh, sir, u and v are disjoint containing fx and gx.
Yes,
So the inverse.
that is right. But the
Uh,
thing is, I mean, U is an open set containing Fx and U is an open set containing Gx. But its inverse image both contain X, right? Correct. U and V are empty. So if we take the F inverse U and F inverse V, then their intersection empty. But we are taking the intersection of F inverse U with G inverse V. I mean, so that's why the intersection is not empty. Understand?
uh, Sir, I did not get because we are taking the elements where both are not equal. So if it is not empty, so it fx and gx both are the same. So it does not belongs to be the complement.
No, no, no. So for by choice, what you have done? By choice, you contains fx and v contains gx, and the intersection is empty. It is by choice, right? Correct. But
Yes,
any
sir.
but anyway, x belongs to f inverse u, and also x belongs to g inverse v, right? I mean, this is obvious, correct?
Yes, sir. Yes, sir.
Yeah. So this is what we have done. F inverse u intersection g inverse v we have done. Understand?
Yes, sir.
Yeah. So that's why it is not difficult to show that f inverse q intersection g inverse v is a substantial expansion. Okay. And also it can be done symmetric way. Since f and g are given, so we can consider the map f cross g from x cross x to y cross y, x1, x2 goes to fx1, fx2. Now since f cross g is continuous, since f and g are given to be continuous, now f cross g, Fourier inverse of diagonal of y is equal to all those x such that fx equal to gx. Now since f cross g continuous and y house drop, so diagonal is closed. So this thing is closed in, I mean inverse of closed. So the x of the fx equal to gs, this is closed in x cross x. Sorry, closed in x. Okay. Yeah. So okay. You know one per simplification, right? Yeah. So now tell me, uh, what is the one point compactification of several natural numbers? I mean, the one-way compactification of several natural numbers is homeomorphic to which space? That is what we need. That's why that is what I am asking. The one-way compactification of n is homeomorphic to which space? That is the question. Okay, think about it. No, what do you think? I shall bear with some minutes. Are you getting any idea how to proceed? Are you getting any idea how to proceed?
Sir, I am not getting any ideas.
Okay, so first let me give the hint. So the one-man computation of this is the set is. So I mean the sequence one half dot 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 including zero is the one-man computation of capital N. So basically, in order to show this, what you need to do, you need to find some map. You need to find some obviously continuous map from N to this set this such that if the set is F, such that image of F, I mean if this set is capital X, such that X minus image of F is singleton. Right? This is what you need to show. Right? I mean this is what you need to show. Am I right? I mean, do you understand?
What is written in the last line, sir?
Yeah, X minus, I mean if X is a this state is the X, then X minus image of F should be 1. We need to check that. Right?
Yes, sir. If you will take f of n is equals to 1 by n.
Yes, that's correct. So N goes to 1 by, yeah. So I mean, so this specifics the one multiplication of capital N. Okay. So yeah. So do you know the metrizability? I mean, do you know the um, under which conditions a given space is metrizable? I mean, in general, topology is metrizable. So under which conditions you know the particular given space is metrizable? Do you know any such condition? Do you know any such condition?
Yes, sir. If x is Hausdorff, then it is metrizable, and there are many other conditions as well that I am unable to recall at this moment.
Okay, so why you think that house job is a metrizable?
Yes, sir.
Why you think that house job space a metrizable? I mean, is there some theorem or some exercise you have done? So the thing is, a house job space, T2 space may not be metrizable.
Yes, sir. Actually, metrizable spaces are Hausdorff, but the converse is not true.
So can I give one such space which is house job but not metrizable? I mean, yeah, think about it. It is not directly obvious. So
Sir, if we will take R
yeah.
omega respect to box topology or something.
Yes, right, correct. Box topology. It is not okay. So why you think that normally box topology is symmetric? Yeah, there is some sequential argument you are going to say, right?
Yes, sir.
Yes, fine, fine. Good, good, nice. Very nice. So, yeah. Okay, so so you already know one definition of regularity normality. So do you know any characterization of regularity other than its definition? Do you know any characterization of regularity other than its definition?
Yes, sir.
Can you please tell me? Can you please tell me? Don't hesitate. Whatever you can remember, just tell.
Sir, yes, a regular space is sir, locally compact.
No, no. The characterization. I mean, characterization means something is regular if and only such a thing holds. That type of statement have you read apart from definition?
Yes, sir. Yes, sir. There was a statement.
Yeah.
Sir,
Can
a
you
space X is regular if and only if you will take any point in the space X, such that there exists a neighborhood of u of X such that X, no sir, for any neighborhood u of X there exists an open set which containing X and also a subset of U such that X uh, belongs to that set which is a subset of its closure, and that will be a subset of U.
Okay, it's very nice, very nice. And same goes with normality, right?
Yes, sir.
Yeah. So using this, consider the last problem.
But sir,
So
I had a doubt regarding this. Sir,
yes,
uh, maybe in the Munker's book they have assumed the T1 axiom also.
okay,
And sir, in the notes the T1 axiom were not there. So
okay.
I
Okay, I understand. The thing is that it is the matter of definition. Okay, some authors choose the space to be housed up. Some authors choose space to be T1. Some authors choose space to be nothing. Okay. So what is the definition? We need to go along with the definition. But the usually most authors choose the space to be T1 or house stroke. Okay, because it makes life easy, to solve some problems. Okay, but if some author don't choose the house roughness condition, then there is no harm. I mean, that is the definition he or she is giving. Okay, so while solving problem or while in the exam of this uh, subject, you no need. Then I mean, whatever definitions are take, you need to take the definition for this course. Okay, understand?
yes,
Yeah, it's a matter of definition, nothing else. So,
okay.
yeah, so consider the problem that,
Like sir,
mhm. Yes,
if
tell.
be it any exam or anything, house roughness T1 property, nothing is given.
Mhm.
So
So
without
there,
them also, if this relation holds, then we can say that the space is regular.
this is, yes, because if you go through the proof of this characterization, then this proof does not use the house roughness at all. Okay, so without uh, having any second thought, you can assume that this regularity and this thing is similar. Okay, and also in the next class, please ask Sastry sir regarding the clarification of this, because I mean, yeah, it's better to ask him clearly that whether should we assume house roughness or not. Okay, because otherwise in exam it will create some confusion, right? Just ask him in the next class. I mean, you can do
Actually,
this.
sir, the classes are recorded, so that's why.
Yeah, okay. You can email him also, no issue.
Okay, sir.
Yeah. you can while putting the email, you can directly mention him, that is at the rate Anand Sastry sir, something like that, so that only he will reply. Okay, otherwise some other person will reply. Understand?
Okay, sir.
Yeah. Okay, so yeah, today is almost to be 9, so I think today it's a. Okay, so let's end here. So just in the chat box, I have shared one Google form link. Please submit the Google form for the attendance purpose. Okay, please do it.
Okay, sir. And sir, I have a question, not regarding this subject, sir. My question is, sir, in the certificate exam, what will be the question pattern, sir?
Uh, as far as I have, as far as I know that um, uh, it will be like 60%. I mean, not 60%. It will be like some object, some tick mark question and some big answer type questions. Okay, but actually, since there is the only instructor and sir only have the right to decide the question pattern, so it's better to ask him directly through the mail. Okay,
Okay, sir.
yeah. And if you want to ask anything directly from the sir, then in the email, I mean, while doing the email, please mention at the rate Anand Sastry sir. Then only he will reply. I mean, he will understand that the learner want to get a reply from him. That's the point. Okay.
Yes, sir.
Yeah. Okay. So please give your attendance.
Yes, sir. Given.
Okay. So yeah. Okay. So okay. So let's stop there. So we will meet on the next Saturday.
Okay,
And
sir. Thank
if you have any doubt, you can ask in the next live session. Okay. Thank you. I am leaving the call.